Hi, in this video I'm going to talk about how to implement CUDA function that can be executed on the GPU. The GPU is also called device, and the CPU is called host. I will start with the simple function which is hello world function. In order to implement this function, or it's called kernel also, which is executed in the GPU, we start with the keyword underscore underscore global underscore underscore, and this tells the compilers that this is a CUDA function. Then after the global keyword we have the return type from the function, and always with CUDA functions the return type is void. And of course, if you need really a return value, then you have to pass a pointer as a parameter, and inside the function you assign the value to that pointer. Then we have the function name as usual, and inside the function implementation we call the CAPI printf to print the hello world message. Now in the main function, let's see how to load this kernel into the GPU. We use the same way as we do with the CPU functions, hello world, the name, and we have these extra symbol, the 3 less than and the 3 greater than. Between them we have two variables, the number of blocks, which defines how many blocks will be launched on the GPU, and how many for this parameter defines how many threads inside each block. In this example we have only one block, and we have one thread for that block, so in total there will be 1 multiplied by 1. There will be one thread launched on the GPU, and so the message will be printed only one time. CUDA device synchronize is a CUDA function used to force the main to wait for the hello world function to be finished, because calling the hello world in the GPU is a synchronous call, and this CUDA device synchronize will block the main function until the execution of the hello world finish. Now to use this API and to define the kernel or the CUDA function, we have to include some header files from CUDA. Let's now compile this code. We will use the NVIDIA NVCC, and the file. Notice that the extension of the file is .cu, because it contains host function and CUDA function mixed, and the compiler will be able to distinguish between each function based on the keywords in the beginning. As expected, the message is printed only once, because only one thread launched into the GPU. And now let's change the number of blocks to 2, and the number of threads for each block to 3. So now we have 2 blocks, each block contains 3 threads. In total there will be 6 threads. So this function is executed in 6 different threads, and so this message will be printed 6 times. Let's compile it again. As you can see, the message is printed 6 times. There is another way to pass the blocks and the threads per block variables using the dim3 data type. From CUDA. So first of all, I define the grid dimension. The grid dimension is define how many blocks and the shape of blocks in like how many blocks in each dimension, x and y and z dimension, and the same way for block. So when I say dimension 3 grid, it means 2 to 1, it means that 2 blocks in the x dimension and 2 blocks in the y dimension, 1 block in z dimension. In total there will be 2 multiplied by 2 multiplied by 1, in total 4 blocks. And inside each blocks also we have 3 dimensions, the x and y and z, and in this case the number of threads will be 2 multiplied by 1 multiplied by 1 equal 2 threads. So the total number of threads will be 4 multiplied by 2, which equal 8 threads in total. So the message should be printed 8 times, as you can see here, 4 and 4, 8. And this is because we launched 4 blocks, and inside each block we have 2 threads. This is this image shows how to distribute blocks and the threads inside each blocks. So first example, we have grid 2 by 1 by 1, which means we have 2 blocks in the x dimension, and the height in the y dimension is 1, and in the z dimension is 1. So in total we have 2 blocks, and inside each blocks the shape is 3 1 1. Also can be written as 3 only, you can ignore the 1 1. So inside each block we have 3 threads indexed as 0 1 2 0 1 2. So in total we have 6 threads. This is another example for grid 2 to 1. It means the x dimension is 2, the y dimension also 2. So in total we have 4 blocks, and inside each block we defined the shape as 3 to 1. So the total number of threads in each block is 6, and are numbered as 0 1 2 3 4 5 inside each block. In order to access this kind of information from inside the CUDA function, there are built-in variables defined in CUDA. These built-in variables include the thread index, .x, thread index, .y, and in this case it will print 2 for .x, 1 for .y. Also we have the index for each block. For example, here this block index is 0, this block index is 1. In x-axis and in y-axis both have 0. So in this example we have grid of shape 2 to 1, so there will be a block with index 0 0 and 0 1 1 0 1 1. grid dimension, and grid dimension should print the shape for the grid, which is 2 to 1, but here I print only the 2 to the x and y dimension. Also the block dimension, the same way, you can print the block dimension dot x, block dimension dot y, and in this case it's 2 multiplied by 1, or 2 in the x-axis and 1 in the y-axis. Let's execute this function. Alright, so as you can see here, thread index 0 1 0 1 0 1 0 1, because inside each block in the x-axis we have 2 threads, or the value of x-axis is 2, and in the y-axis it's 0 always, because this is the height for the y value. And for block index we have 2, so the values will be different in each thread between 0 and 1. So 4 threads has the value 1, 4 threads has the value 0, and for the y-axis also the same, 0 0 0 0 1 1 1 1. And you can see each thread prints the correct dimension for the grid and for the block as we passed it. Let's go to the second example. This is this example we use the CUDA device probe data type or struct in order to retrieve information for about the CUDA or the GPU's capabilities available on the machine. This CUDA API used to retrieve how many GPUs available on the machine, get CUDA device count, and we loop over each device ID from 0 to up to count -1, and we use this API to get device properties, and for each device we'll pass the proper index. These are the information that we can retrieve from this data struct. Let's compile this code. So as you can see here, the number of available GPUs equal 1. This is the name of the GPU. This is the compute capability. This is the major version. This is the minor version. Through this version you can go online and see what are the properties of the GPU. Here are more information, including clock rate, global memory, constant memory, and it defines also what is the maximum threads per block. So for each block, when you pass or when you call the CUDA function, the maximum number of threads in each block should be 1024. And here also restriction for the grid dimensions. Now let's go to another example, which is adding 2 integers. So here we define the CUDA function the same way we start with underscore global. This will tell compiler that this is the CUDA function. The return type is always void. Add two integers. This is the name of the function. The first parameter is the pointer to the source, first source or first variable. The second parameter is pointer to the second variable, and the third pointer is where we will store the result. In the main function, first of all we will define or allocate memory for each of the host or the CPU variables A and B and C using the C malloc API. Then we have to allocate a corresponding variable on the GPU. We will use the CUDA malloc API, and C takes the address of pointers. So we define 3 pointers and we allocate them on the GPU. So these pointers are pointers on the GPU. Then we initialize the host variable A and B. So A equal 5 and B equal 9. So the result should be equal to 14. After that, we need to copy these host data we initialized into the CUDA or into the GPU variables. So this will copy A into the device underscore A, and this will copy the value of B into D underscore B. And using this API also we have to pass this flag, which is CUDA mem copy host to device. This will tell the runtime that the copy direction should be from the host to device, or from CPU host into the GPU device. Now we will call the function, and as usual we pass the two parameters, blocks. The number of blocks, in this case only one thread is needed, so we pass one for the number of blocks and one for the number of threads in this block, and we pass to the function the device variable DA, DB, DC. And using the synchronize function, we will wait for the results to be finished. And after the execution of the function is finished, we need to copy back the results from the device or from the GPU into the host variable. So you see here the flag or the direction is the opposite, CUDA memory copy device to host, which means copy from the GPU to the CPU. Now we will print the results using after we copied the value into the host variable C. We need to print to make sure that the result is correct. And after that we will free the host variables and the CUDA variable. See that for the CUDA variables we use CUDA free instead of the normal C API free. Now let's compile this function. So as we expect, the result is correct. 5 plus 9 equal 14, but this operation is executed, or it was executed on the GPU. Now let's see the implementation of another function called print array. So we are trying to print an array of integers using the GPU. First of all, we have to add the global keyword at the beginning, then void return type, and this is the name of the function print array. We pass two variables or two parameters to this function, a pointer or the array of integer and the length of this array. Before we see how this function is implemented, let's go to the main function and see how memory allocation is happening. First of all, we define the length of the array. In this case, I set it to 20, and of course you can add any number. The number of bytes equal to the length of the array multiplied by the size of integer, because the array type is integer. Now we allocate the array on the host memory. So this is a pointer to an integer, which is the array we have in the CPU or on the host side, and we use the C API malloc to do that, which takes the number of bytes and it returns. Here we are casting the return type into integer pointer. Then we need to initialize this array. Each entry of the array takes a value from 0 to 20, or from 0 to 20 minus 1, which is 19. So the first entry will be assigned the value 0. The second entry will be assigned value 1, and so on. So this is for the host array. Now we need to declare a corresponding array on the GPU side. In order to do that, we use the CUDA API, CUDA malloc, and we pass it a reference to device pointer and the number of bytes. So by now we have both the host array and the CUDA or the GPU array allocated. Using the CUDA memcopy, we will be able to copy the host array into the device array or the CUDA array in order to be able to access it from the CUDA function. So CUDA memcopy will copy the host array into the destination, which is the device array, and this is the number of bytes, and the last parameter is a flag to tell the direction of the copy. In this case, it's from the host to device. Now let's see how to launch or call the CUDA function. As we do define two parameters or two variables, which is the number of blocks we have in the grid, in this case 2, and how many threads inside each block. So we have 2 blocks, 3 threads in each block. 6 threads will be responsible on printing the elements of the array. Each thread will take some will be responsible on printing parts of the array. So here we call the print array, and CUDA device synchronize will wait for the function to be finished. After that we will free both host array using the C free API, and we use the CUDA free API to free the device array. Now let's go and see how the implementation of the print array function. First of all, we need to know this thread which index can access. In order to do that, we have this ID, global ID or I, equal to block index dot x multiplied by block dimension dot x added to it thread index dot x. So this equation will give the index of the entry in the array. As you can see in the picture, let's say we need the index of thread number 1 on block number 1. Using this equation, block index dot x equal 1 multiplied by block dimension dot x. In this case it's 3, because each block has 3 threads. So 3 plus thread index dot x, we said it's 1, so 3 plus 1 equal 4. So the global ID will be 4 in this case. So this thread will print the index number 4 in the array, and as you can see here, the values 0 in the first block is 0 in the global array, and the value 1 in block 0, it has global ID 1, 2, 2, 0 in the second block, 3, 1 equal 4, 2, 5. But there are the remaining entries on the array. We will use also these threads to access them. This is why we have this addition, which is it's kind of offset. Grid dimension dot x is equal to 2, because we have 2 blocks. Block dot dimension dot x equal 3. So this is kind of the total number of threads in the whole thread, which is the whole grid, which is 6. So after let's say the thread prints the value with global ID 4, it's add 6 to 4, which equal to 10, and the thread is will also print the index 10, then 16, then at 6 to 16, 22 is greater than 20. This is why it will exit this while loop. And the same for the other thread, it will start with the value 1, then the value 7, or sorry, the index 7, then 13, then 19. And for the third thread, it starts with index 2, then 8, then 14, then it exit, and so on. Let's compile this code. As you can see, all the numbers from 0 to 20 are printed on the screen. The reason we see new line, it's because of this line. Maybe this is incorrect to add, so let's compile it again. As you can see, the values from 0 to 20, which are the entries of the array printed to the screen, and they are not sorted because threads are running on parallel. Alright, let's see another CUDA example, which is adding two arrays in the GPU and stores the results on another array. This is our function add arrays, and as usual we start with the global keyword, then void as a return type. This is a function name add arrays that takes three parameters, or takes three arrays A, B and C. A, B are the input array, and we will add each entry in A and B and store it on the array C. Integer n is the length of these arrays, and as usual we start with calculating which index in the array this thread can access. To do that we have integer I equal block dimension dot x multiplied by block index dot x, then we add thread index dot x, and as we remember each block has multiple thread. Each thread has local index, so we need to map these local indexes into the array indexes. In this case, for example, block 1 in thread index 0 will access array index 3, block 1 index thread index 1 will access array index 4, and index 2 will access array index 5, and so on. Here we have the addition operation, the normal addition for the entry at index I. So A of I plus B of I, we store it at C, the output array C I, and here we have this offset. So I plus equal grid dimension dot x multiplied by log dimension dot x, and this equal the total number of the threads, and we keep looping until I is greater than n. So we do this as we said before, that each thread can handle multiple entries in the array. This is because the number of threads sometimes is smaller than the length of the array. So for example, thread 0 in block 0 can access indexes 0 plus 0 plus 6, which is the total number of the threads. So it can access also index 6 and 12 and 18 for this example. Now let's see this. This is just the host function that will verify that the result that calculated in the GPU is correct. It takes again the same arrays A and B, and also the output array for that resulted from the GPU, and verify this array has the correct results. So here we calculate in the CPU side A of I plus B of I, and we verify that the results from the GPU is correct. If any entries is not equal, we will print GPU result is wrong, and we return. If all of the entries are correct or are equal, then we will print GPU result is correct. Now let's see the main function implementation. First of all, we define the length of the arrays, which is 2 to the power 16, and the number of bytes equal to the length of the array multiplied by size of integer, because the arrays are of type integer. First of all, we need to allocate the allocate memory for the three arrays on the host side using the C malloc API. As usual, we pass it the number of bytes, and we cast the return value, which is void start, into int star, and we do this for A and B and C arrays. Then we need to initialize the input array A and B into some values. In this case, I assigned each entry to a value equal to I, looping from I to N. After that, we need to allocate the corresponding arrays, but on the GPU side. And to do that, we declared three new pointers. D stands for device, so it's just a name. And instead of using the C malloc API, we need to use CUDA malloc API. We pass it the reference to the pointer and the number of bytes that needs to be allocated on the GPU. So now, after we allocated the three arrays on the GPU, we need to copy the values or the arrays that we initialized in the host into the CPU, and we do that using the CUDA mem copy. This is the destination, which is the device array, and this is the source, which is the host array. This is the number of bytes, and this flag tells the direction of the copy. In this case, it's from the host to device. We do this for both array A and B. Now let's see how to launch the kernel. First of all, we need to define the number of blocks. So here we have blocks in grid equal to 4, and we have thread in each block equal to 8. Of course, you can play with these numbers. And here we call our CUDA function. As usual, we pass it the number of blocks and the number of threads in each block, and we pass it the three arrays A, B, DA, DB, DC, and the length of each array. And we wait until the CUDA or the GPU finish execution of this function. Using this CUDA device synchronize will guarantees that the main function will wait until the GPU finishes the execution. And after that, we need to copy the results from the CUDA side into the host side. We do that by using again the CUDA mem copy, but we flip the direction. Now the destination is our local or the host array C, and the source is the device array C. This is the number of bytes, and here the direction is from the GPU to the host or from device to host. Now we call our function to verify that C is actually carrying the expected results. And after we're done from that, we need to free all the allocated memory in the host side A and B and C using the C free API. And also we need to free the memory allocated for the GPU pointers using CUDA free API. Let's compile and run this code. We will do this again using the NVCC. Alright, This means that we successfully run the addition of the two arrays into the GPU, and the result is correct. Alright, let's move to another example, which is the max number of divisors. In this problem, we are given an integer n as an input, and we need to return the maximum number of divisors for all the numbers from 1 to n. So for example, if n equal to 8, we need to loop over all the integer from 1 to 8, and for each of these number we calculate how many divisors for that number. The divisor is suppose we have a and p. P is divisor for a if a model b equal 0. So for number 1 we have one divisor, because for all number from 1 to 1 there is only one number. 1 model 1 equal 0, so it's only one number, so the result will be 1. For 2 we have two numbers less than or equal to 2, which are divisor for number 2. For 3 we have two number 1, 3. Notice 2 is not a divisor because 3 modded 2 equal 1. It's not 0, so we have 2. For 4 we have three numbers 1, 2, 4. For 5 we have 2. For 6 we have four numbers 1, 2, 3, 4. Sorry, 1, 2, 3, 6. So the count equal 4. For 7 we have two numbers. For 8 we have four numbers, and the final result would be the maximum of among all of these counts. So 1, 2, 2, 3, 2, 4, 2, 4. The maximum equal to 4. So the input of the function equal 8. The final result will be 4. In the example we will show three versions. One is the algorithm implemented on the CPU, and two versions for GPU implementation using CUDA. Let's start with CPU version. First of all, we have this helper function, get number of divisors. It takes integer number and it returns how many divisors for this number. This is enhanced version of the big O of n version. Instead of looping from I to n, we are looping from I to square root of n, and for each I we check if and model I equals 0, count plus plus. Also if this condition happen, we increase the count, and we return the results for this n, which is the number of divisor of n. So if we given 7, the return function for this should be 2. If we give 5, it's 2. For 4, it's 3, and so on. This is the runner for this function. So given the input n equal to 2 to the power 20, we need to find the maximum number of divisors for all number between 1 to n. So we have to loop from 1 to n, and for each number we calculate the number of divisors using this function, and we take the maximum among all of them, and it would be the final result when we print this result. Let's move to the GPU, the first implementation on the GPU using CUDA. So the same way we have this helper function in the CPU, we need something similar but on the GPU sides. We can't call this function from the kernel function or from the GPU, because this is a host function. It can only be called from any other host function like the main or like this function. So we came with this keyword underscore underscore device underscore underscore, and this tells the compiler that this is CUDA or this function can only be run or can be called from kernel function in the GPU. Notice the difference between the device and the global. With the global, like both functions are functions that should be run on the GPU, but the global function is initiated from a host function like the main, as we saw previously, while the device function is only can be only called from other GPU functions like this one. So this is our kernel function. It takes an array of integer. Let's see how to declare this array in the function or the runner of the kernel function. First of all, we declare the bytes, number of bytes equal to the blocks, which is we have 1024 blocks, and we have each block contains 256 threads. So the array length that will be passed to the kernel function will be equal to the number of blocks, which is 1024. And first we declare this array on the host memory. Then we need to declare a corresponding array on the GPU using CUDA malloc, and we call our function that calculate the maximum number of divisors and fill this array. We have, as we said, 1024 blocks. So this array, each element contains the results of sections of numbers from 0 to, or from 1 to n. And we wait for the function to finish. We copy the result back, and we let the CPU take the maximum of this small array of length equal to the block numbers. Then we free both the host and the CUDA memory. Let's look at the implementation of the kernel function. As we said, it takes an array of length equal to blocks. So each block will be responsible of filling one entry in the array by calculating the max number of divisor among set of integers from 1 to n. Remember, n equal to 2 to the power 20. First of all, we declared memory, cache memory. This memory has 256 elements, which is threads per block, and we declare this memory as a shared memory. So this new keyword is CUDA keyword to tell that this is a shared memory. The shared memory is a memory that can be accessed from all the threads inside the block. So we have threads per block equal to 256 threads. All those threads can see this memory in the block, and we have 1024 blocks. Each block has a copy or declares this kind of memory. It's like static memory that can be accessed by all the threads inside each block. And as usually, we need to determine the index in the array that this thread can access. And initially we have each thread setting its element to 0. So all the threads 256 will set their entries into 0 so the cache it's like setting all elements on the cache or the shared memory to 0. Now we need to loop as usual until we get greater than n. You remember this offset, why we use it, it's the same way. And for every element we calculate the number of divisors, and every thread assign or calculate its set of numbers, and set the corresponding entry in the cache to the maximum. This new keywords after we finish the while loop, it's underscore sync threads. It means all the threads on this block, which are 256, wait until they finish. So by here we have an array of 25, which is the cache array. After finish calculation, each entry has the maximum of set of number, maximum divisor counts, of course. And now we need to calculate the maximum of all of these entries in the cache, so that at the end we have one value and we assign it to the block corresponding block number. So the idea here is to use parallel reduction. This is why we call it parallel reduction. Let's say this is our cache memory, and each entry has the maximum value, and we need to calculate the maximum among all of these. So every thread will be responsible on calculating two values. Let's say this thread will calculate the max of this, and store the result on the first entry. The second thread will be responsible in calculating the max of this thread and this thread, and store the result in this element. And by the end of the first stage we have instead of this number of entries, we have half of them. Then we keep looping. In the next stage we divide it by 2 until we have only one element, which is the maximum of all of these elements. This is why it's called reduction. First of all, we start with I equal to threads per block divided by 2. We keep looping until I equal to 0, and by the end of this we will have the first element of the cache having the maximum among all of these numbers. Notice that at every stage we need to use again the sync threads to make sure after each stage that the array has the correct state of maximum values from this stage, and only after that we can move to the next stage. And here we have remember the cache, the first entry equal to 0, so only one thread is sufficient to assign this value to the corresponding block index, and block index is any value from 0 to blocks, which is 1, 0, 2, 4, and we assign the value of cache 0. And remember, after we return the value to the host, we copy it back to the host memory. We let the CPU calculate the maximum among all the array elements on this global array, and we store the result on the GPU result, and we print it. So this is the first way of implementing this code on the GPU, which is which use parallel reduction, because as we saw here, and at every stage the number of elements will decrease to by half. Alright, so this is our first version of the GPU implementation. We will implement the same algorithm, but we use a new method called atomic. So in this method, instead of declaring the array of the number of blocks, we will declare only the final results. So the host result will declare only one integer, and the corresponding CUDA or the GPU will allocate only one integer value, and we launch the kernel here. We wait the same way, and we copy back the results as the final results. No need to loop over the an array here, so the CPU will not do anything. The GPU will do the final results, and we clear our memory. Let's see the implementation of this atomic way. Here it takes the pointer to the integer. As usual, we calculate the index in the array, and the same way here we do the offset also. So we loop until I equal greater or equal to n. So for each I, the same way we calculate the number of the divisors. And here is the trick. We use atomic max. Atomic max, it's similar to atomic operation on C++, so it's safe access and update to the result value. So all the threads are safely accessed and update this value. It's kind of lock and update the value, then unlock. So it's CUDA API that is a thread safe, and all the threads can update this global variable directly. And if you feel there is like high pressure, in case you have hundreds of thousands of threads accessing the same entry on at the same time, then this will decrease the performance. In that case, you have to split the operation to use the cache operation first, cache method first, then later on you have to loop over that cache array using atomic max, and you update your final result. But this implementation is very simple, and it's good enough. So by now we implemented the three ways of calculating max number of divisors. In the main function, we will call these three ways: the CPU and the GPU parallel reduction, and the GPU using atomic. And we use the simple execution time calculation using chrono library by putting start and stop and calculating the duration. Let's try to compile and run this code. Alright, so this is the results. The max number of divisor equal 240 in the CPU for n equal 2 to the power 20, and the same result you will have for both the GPU versions, 240, 240, 240. And notice the execution time in the CPU is much higher than both version on the GPU. This shows the power of GPU on executing the algorithms and also here you see the atomic version is much faster than the parallel reduction version. This is because we did not there was no need to declare that extra array. We directly updated the global results without the need from the CPU to allocate a memory and loop over that memory to calculate the final result. Now let's move to the final thing. So I want to show you that it's recommended in general when implementing CUDA function to do an error check around all the CUDA methods API, CUDA malloc, CUDA memcopy, any CUDA API. It's recommended to do an error check because these functions return error status, and you have to implement this function. So this function simply checks if the return status from the function equal to CUDA success. If there is an error, it prints to in which line and in which file. And here I exit the application. So for example, here instead of declaring I use CUDA malloc, and instead of assigning the number of bytes, I assigned 0. So later on when doing CUDA memcopy, it should give an error. So let's compile this code. So our function catch that there is an error invalid argument in error handling line 82, and by backtracking the error we discover that there is problem here, and we have to assign the number of bytes. So let's compile again and run the same function. Now the GPU result is correct. This is the same function we implemented in the past, which is adding two arrays. So the whole idea here that it's recommended to check the status of the return value of all the CUDA APIs in your application. By this you will catch all the errors. That's all. Thank you.